Hello everyone, my name is Naren and in this session, let's learn rate limiting algorithms which also works with distributed system. Scenario 1, consider you have an application which is deployed in a server and then it is working fine. Someday you started to see sudden increase in traffic, say for example 10 times the normal traffic. And all of the traffic is from bots. Scenario number 2. Consider you have a product which provides APIs for machine learning or report generation or weather information. You also want to make money out of these APIs, right? So you have a production enterprise APIs, but you also want to let developers try these APIs first and then they will purchase it. For that, you need to allow developers to access these developer APIs. Say, for example, 10 APIs per minute or 100 APIs per hour, something like that, just for them to try and integrate with their application and then they will purchase it. How do you do all of these things? For both the scenarios, the solution is a rate limit. Rate limiting protects your APIs from overuse by limiting how often user can access your API. Once the user's quota is finished, either the requests are dropped or rejected. And it is very important for many important reasons or benefits. For example, UX. Say, for example, you have an application in which some users are overusing the APIs of the application. In that case, the other users will get affected. So, user experience, if you want to maintain quality of service or better user experience, you need to rate limit from users using these APIs unadventurally or unknowingly or intentionally. And the second one is security. Say, for example, people might try brute forcing login APIs or some other APIs like promo code or some APIs like booking or something like that. So you need to rate limit to protect yourself from being attacked by hackers or something like that. And also operational costs. Say, for example, your application is enabled for auto scaling or pay as you go service. What if users are bombarding requests to your service just for the fun or by mistake? In that case, your server will automatically scale or pay as you go bill will increase. So to reduce the operational costs, also you need to rate limit. So what are the different levels at which we can rate limit, or what are the different kind of rate limiting we can do? First one is user-based rate limit, in which you know that for a particular given user, how many requests you are going to allow per minute or per given duration. That's called as user-based rate limiting. And the second one is concurrency or concurrent rate limit, in which you know exactly for a given user how many parallel sessions or how many parallel connection is allowed. In this case, the main advantage is it will help you to mitigate DDoS attacks using concurrent rate limiting. And the third one is location or IP-based rate limit. This rate limiting helps you when you're running a campaign dedicated for a location or when you're running some event dedicated to a given location, in which you can rate limit all the other location except the location which you are targeting. In that way, you can provide high quality of service for the location which you want to target, and you can allow very few requests for the others. That way, the location at which you are targeting will get very good quality of service. And the third one is server-based rate limiting. So this is a weird case, but it might come handy on certain kind of situation where you have defined a server is dedicated for a certain kind of service, in which you can rate limit the different services the server provides. That way, it will help you to enforce some kind of rule on a server. So let's see what are the different kind of algorithms available to do rate limit. So the first algorithm which we are going to take a look at now is token bucket. Consider we are limiting our APIs to 5 requests per minute. So how does this token bucket work? For every unique user, what we are going to track is we will track the last time at which the request was made and also the available tokens. That is, in this case, since we have about 5 requests per minute, so we have 5 tokens left. And all this information should be stored against the user ID. So in this case, I'm going to take U1 as the user ID, okay? So every time the request comes in, our rate limiting application or software should do two things. First one is fetch the token. That is, it should go to this bucket and then fetch the token for that particular user. Usually we use Redis as the token bucket because it is in memory and faster to access. And also the second thing it needs to do is update the token. So once it accesses the token, once it learns that we have enough token left, so it can make the request, and also afterwards it should update the token to the latest token available. Okay, so I'm going to explain how it works. Say for example, a request comes in at say 11:01 10th second. Okay, in this case, what rate limiting algorithm should do is it should go and check. So we know that user one is making request. For user one, what is the data is available? So that is 11 o'clock 01 minute and 05. That was the last access, and the available token is 5. Okay, now this record says for this particular minute was the last made request, and they have 5 tokens left. That means that we can serve the request, right? So it will serve this request, and also it will update the tokens. Okay, since we have made one request, let's update the token to 4. Okay, consider the same user one made one more request at 11 o'clock 01 minute, say 25th second. In this case, again, when the request comes in, you need to check user one and the data available here. Okay, forgot to tell you that when you update this, we also need to update this timer. So the time also. In this case, the first request was made at 11 o'clock first minute and 10 second. We have to update that. When the second request is made, okay, that is at 11 o'clock 1 minute and 25th second by the same user, okay, we have to go and check the data for the user one. In this case, we have 11 o'clock, the last access request, 11 o'clock 1 minute and 10 second, and the token is 4. That means that still we have token to serve. Okay, that means that we'll reduce this and serve the request back. So we can do the same for the same minute, that is 11th hour, first minute, we can serve another 3 requests because we have 3 tokens left. So after serving 3 requests, this token will become 0. Okay, that is the ideal situation where we are getting more than 5 requests per minute. There could be possibility that we won't get more than that request. So consider we only got 2 requests, that is at 10 second and 25 second. We still have 3 counters, 3 tokens left. So the next request which comes in, say for example, came at 11:03 minute and say 10th second. So okay, in this case, what we need to do, we need to access the information over here. That means the token information. So for the same user U1, if you see that here, we have the time 11:01. That means that we get to know the last access time was 11:01. So what we need to do is we need to refill the token at that point of time. So we need to update the time from 01 to 03, and the token we have to reset it to 5 because we know that this is the first request which we are making at this particular minute, and the rate limit number of requests is allowed is 5, so we updated it to 5. Now we also know that since we have 5 token, we can serve this response. So let's serve, okay, and decrease this token to 4. If the next request comes in at the same minute, that is 11:03, say some seconds, say 15 second, what do we need to do? Again, check that information, 11:03 minute, and we have 4 token. That means we can serve the response. So decrease this token from 4 to 3. We can keep on doing the same thing. So we have to do the same for each and every user. That way, we know that how many tokens are left and how many requests we can serve. And when this token becomes 0, if there are any more requests coming at the same minute, okay, consider this is also updated to the last access time. So when the next request comes in, say for example at the 11:03 and some 22nd of same minute, right? So now what we need to do, we need to get that information, and we check that how many tokens are left. Since it is updated to 0, that means that we can't serve the REST request and response. And that's why we are going to drop this particular request and we are not going to serve that request. And even if more requests are coming for the same minute, we're not going to serve it. So this algorithm is memory efficient as we are saving a less amount of data per user in your application. But the problem is in distributed environment, it could cause a race around conditions because for the same user, if two requests are coming in different application server, both might try to update the same thing or same record, right? That could cause problem. So the next algorithm is leaky bucket, okay? How does that work? Yeah, I'm going to explain. Consider this as a bucket, okay? And it can hold three requests at any given point of time. And this is where the requests are coming in, and this is where we are going to process the request. So we will have a request processor over here, which runs at constant time. That is up to you, okay, your calculation. So consider this request is going to serve like one request per second, okay, on the other side of the bucket. And here is the entry point of the bucket, okay, is like first in and first out, like, okay, that is something like queue, okay. When the requests are coming in, if the queue is empty, the very first request will come and sit here, and then the second request. So meanwhile, the request processor will be processing this request. If there are more requests coming in, the bucket will fill immediately, okay, before even we process it. And the extra requests like fourth and fifth request, seventh and eighth request will just overflow from the bucket. It can't even be, we can't even allocate or accommodate space for those requests over here. Once on the other end of the bucket, if the first request is processed, so we will have one space empty, two will come here, three will come here, and we have one space empty. So maybe this fourth, fifth, seventh, eighth request are already spilled out of the bucket. So we have a ninth request coming in now, and that will get the space. And then we process it continuously. So since on the other end of the bucket, we are processing the request at a constant rate, at any given point of the time, we have the resource, or we only serve three requests at any given point of the time. So that way, even though we are getting burst of requests, that is thousands of requests at any given point of time, because of this kind of design, our servers are not affected. So that will smoothen out the burst traffic. So the next algorithm is fixed window counter. This is the simplest of algorithm in which we have a counter. We keep on incrementing the counter for every request. And when the counter exceeds the rate limit, we are going to drop all the requests which are coming in. Say, for example, we want to have a rule like 10 requests per, not second, per minute. Say something like that. So 10 requests per minute. In this case, how do we implement? Say something, we again use Redis. So we'll have to have a key, something like this, user one and the window. So the window is like minute as a window. At say 11th minute, we'll start from 0. When the request comes in, when the first request comes in, you increment the value from 0 to 1 and keep on doing until it reaches to 10. Once it reaches to 10, you're going to drop all the requests. If the request is coming on the same minute, that is 11th hour and 0th minute, okay? And if the next request comes in, so the key will be 11:01 and starts from 0. And then for each and every request, this number will keep on incrementing until 10, and later on the request will be dropped. It is memory efficient because we are going to have a key for each and every window and a user, and also a number which increments until the rate limit, okay? And that's how it is memory efficient. But there is one more problem. Say, for example, you have a window. Say this is 0th minute, this is first minute, and this is second minute. Consider we are getting about more requests in the end of the minute. Say, for example, we are getting tons of requests at this point. That is when the first or the 0th minute is about to end. That is about 55th second or 59th second. Say, for example, we got about 20 requests. In this case, at this particular window or this particular couple of seconds, we get more requests. And also if the request continues, and in the beginning of the next minute also we'll get the request, right? So the server will be overloaded. So what we tried to achieve was 10 requests per minute, but actually we got 10 requests. So out of 20 requests, we only accept 10 requests, right? So we got 10 requests at 55th or 59th minute. Sorry, 55th or 59th second. That means that the server is overloaded here. And also the traffic is not smoothened. In case of Leaky Bucket, the traffic is somewhat smoothened because it is kind of buffering using queue or a bucket, right? But in this case, it doesn't happen because we accepted 10 requests in the end of the minute because we have 11:00, and we also accepted 10 requests in the beginning of the next minute because we had one more window at the next minute, okay? That is 11:01. So we accepted, in the next minute, we accepted 10. In the previous minute, end of the previous minute, we accepted 10. Totally, we accepted about 20 requests in about duration of 5 to 10 seconds. And that is bad because we always wanted to maintain about 10 requests per minute. So now that we know the problem with window-based counter, how do we solve this problem? So the solution to the problem is, instead of calculating the rate in each and every windows, let's calculate the rate in real time. So the algorithm is sliding logs, okay, in which we're going to use hash table or Redis, anything which can store key and value pair. Say for example, we'll have to have a key again based on user ID, and yeah, just by user ID. So we don't need to have any time information here. So we have user information or user ID over here, and we'll take a big list. Okay, consider we have taken a big list. In this case, for every request, we need to append a log into this array. For every request which is coming in from this particular user, we need to keep on adding the entry to this big array. Consider we have added entries. So these are the entries which are added to the big array. That means that these are the entries for all the requests which you have received so far. Each entry should also contain the timestamp at which that particular request came in, okay? And what we need to do for each and every request, for every request which comes in, then what we need to do is, we need to access this array and then filter out all the entries which are older than 1 minute. Say for example, our rate limit is suppose 10 requests per minute, okay? In that case, what we need to do is, we need to sort this particular array and then filter out all the requests or all the entries older than 1 minute, because we have the rate limit of 1 minute, right? So we have to filter, we have to remove all the entries which are older than 1 minute. So consider these are the older entries, okay? So let's remove that, okay? Consider we have removed. So out of the remaining entries, we need to count them, how many of the requests have been served in the last minute. So in this case, 3, 3, and 7. Totally, we have about 7 requests or 7 entries in the remaining in this array, which belong to the last minute. No matter you are accessing at 10 o'clock, 30 minutes, and 30 second. So we are going to look until 10 o'clock, 29 minutes, and 30 seconds. So exactly delta is 1 minute always. So we're going to get all the entries in that 1 minute window, which is exactly calculated right at the time the request comes in. In that case, we get the real time entries for the last minute. Okay, in this case, we have 7. That means that we can still allow 3 more entries here, or 3 more requests to be served. Okay, consider we had more entries. Okay, instead of 7, consider we had 8, 9, 10, 11 entries. In that case, okay, when we count the remaining last 1 minute's windows entries, so we get the count 11. That means that we have already served about 11 requests in the last minute. That means that we can't serve more. That's it. So every time if we keep doing this, we get to know the real time count of how many requests we have served in the last minute. Based on that, we need to check with the rate data we have. If it is if these entries are more than the rate limit, so we're not going to serve. So everything is good. But there is one problem here. So look at the data for each and every user, for each and every API for a particular user. So we'll have to store as many entries, which is almost equal to the rate limit. That is, if you have 10, so we'll be obviously saving 10 entries in the list. So consider if there are like tons of users or millions of users accessing, we'll be having millions of user into rate limit, that many numbers of entries in your hash table or Redis. So that is kind of bad because here we are consuming more memory. But how do we solve that? Let's learn sliding window counter. So this is the optimization algorithm, which is almost similar to sliding logs algorithm. But in this case, we are going to optimize in the memory side. So we're going to make this algorithm which consumes less memory. And how do we do that? In sliding logs, we used to store each and every entries, which is for each and every request in an array, right? For the last minute. But in this case, we do the same thing, but instead of saving each and every entry for each and every request, we are going to save less entries. If two requests are coming in same second, so we're going to increase the entries counter. Okay, let's learn how to do that. Say we're going to again use hash table or Redis. We'll have to have a key that is obviously user ID, and then we'll again have a array. So in this array, we'll have to have entries. So these entries are, say for example, we got a request at 11, okay, 30, and first or second one. In that case, we'll have to have an entry which has the same timestamp, okay? And then if we get one more request at the same time, that is same second, instead of just saving the entry, in the entry, what we are going to save is, we will save timestamp plus counter. In this case, we got two requests for the same time and the second. So we're going to keep the counter to 2. Okay. And if there is one more request which comes in at 30, says 03, we'll have to add one more entry. But in this case, we'll save the timestamp, and there is only one request at 11:03. That is at 03. This was at 01. Okay. At 03, we have 1. Okay. If there is one more request which comes in at the same second, that is 03 seconds, so we'll increase this counter to 2. Or if there are more requests coming in, say 5 requests came at the same time, so this counter will be 5. And we are going to keep adding the entries like that. And for each and every request also, we need to sort and filter out the entries for the last minute, just like the way we did it in sliding logs, right? Similarly, we have to get all the array entries in all the array, and then we have to filter for the last 1 minute's entries, and then rest we need to discard. Okay, consider we discarded this because it was for the last, it was beyond the last minute. So we discarded this, and we have, say we had more entries. Say this counter to counter at this is say 4, and this is 1, and say something like that. So in this case, we have 3 entries, and then we need to count the counters inside these entries. So 5 plus 4 plus 1, that is 10, right? That means that we have served 10 requests, okay? 10 requests in the last minute, which is equivalent to the rate limit which we have. That means that we can't accept more requests further, okay? If one more request comes in, okay, what we need to do is we need to filter again. If it is like, if when we do the same calculation of when we filter, if this entry is removed, in that case, we'll get how much? 4 plus 1, that is 5. That means that we can accept another 5 requests in that window. So we can serve if you want. If the count exceeds or equivalent to the rate, we can discard. So if you see here, the number of entries which we have is reduced substantially because we have a counter here. Instead of having each and every entries, now we have few entries. Unlikely earlier in the sliding log, we used to have at most as many entries in the list, which is almost equivalent to the rate limit, right? Now we only have couple of entries because we are having a counter inside of it. So that's how this is memory optimized solution over sliding logs. So far, we learned a couple of algorithms to solve the rate limit problem. Now, these algorithms works well on a single server setup, but when we have a distributed setup with multiple nodes or multiple app servers or multiple rate limit services distributed across different region, it won't work. The problems are, first one is we will face inconsistency in the rate limit data. And the second thing is a race condition. Say, for example, in this setup, you can see that this particular setup is in a different region called, say, we call it as R1, and this is in region 2. So for every region, we need different load balancer, and also we need a rate limiter coupled to the load balancer. So I have just written separately just to show you guys while explaining. Okay. Similarly, we have separate load balancer for region 2, and there is a rate limiter. And this is the app server for this region, and this is the app server for this region. Okay. And this is either Redis or Cassandra, which holds the rate limit data, which we discussed in the previous algorithms, right? So that data, key value pair data, will be saved in this DB. Okay. Because we want to enforce a global rate limit. Okay, if we don't have this system, we should be saving the data locally. Okay, if we don't have this data storage, we'll be saving the rate limit data locally. That is like local rate limiting. Okay, but as a whole system, we have to control the rate limit. We don't know the user at high level of concurrency, the same user request might be forwarded to different regions. Say in the same second, if this same request from, sorry, multiple requests from the same user is going to multiple regions, okay, what happens? Both requests will go to different load balancer at the same given time, and it goes to rate limiter, and rate limiter decides based on the data which it has in these nodes, and then it allows requests to forward it to app servers, and we get the response back. Okay, so where is the inconsistency? Say suppose we are only supposed to send allow 5 requests per minute. In this case, consider for this particular user in our node. Okay, so we have, say in this case, in both the nodes we have for u1 4, for u1 4, so the data is replicated in both. Now for example, if two requests are fired from the same user and both requests go to load balancer and load balancer forwards to rate limiter, and now what rate limiter does is it queries the Redis or Cassandra and gets the latest rate limit count. Okay, that means that for that user, so we have so far served 4 requests. That means that we can serve one more request. So what rate limiter thinks is, so we can serve one more request. So what rate limiter does is, it will allow both the requests from both rate limiter, because both of the rate limiter, when it queries the nodes, they both get 4 and 4. Both of them think we can still allow one request. So they both forwards the request to app server. So essentially, we are serving 6 requests, but we had a rule like 5 requests only per minute. So this is inconsistency. How we can solve this problem? So we can solve this problem by using sticky session load balancing in this load balancer. In that case, for this particular user, we will always, no matter what, we will always redirect the request to the same application server using the same load balancer. Okay, that way the request from the user one will never go to a different region or different load balancer and rate limiter, so there will be no confusion. The problem with a sticky session is it is not well balanced design, or it is not fault tolerant design, because when all the requests from the same user is going to one app server, the load on this server will increase substantially. And this server is free, still we'll be bombarding requests from user one to app server. So ideally we will avoid sticky session kind of load balancing. So one more way to solve this problem is using locks. Okay, so how do we protect the race condition? So I explained you the data inconsistency, same way race condition occurs. So how do we solve that? By using locks. So suppose anytime any number of rate limiter access the data for a particular user, they will lock it, and once they access the data and update the data, then only they will release the lock. Say for example, if there is a request file from user 1 to the load balancer, and the request is going from load balance to rate limiter. Okay, in this case, if this rate limiter want to access the data which is of user 1 from this Redis or Cassandra node, he will put a lock on this particular key, so that if any other rate limiter like this one or any other number of rate limiter is trying to access the data for U1, they can't, because the lock is with this guy. Okay, that way we can protect this race condition or inconsistency. But the problem with that is it will add couple of extra latency to the round trip time of the request. So for example, let's go back to the same scenario. When user 1 fires two requests in parallel and both requests are going to different region, they both hit load balancer, okay, and both will forward to rate limiter. So the very first one who reaches, who acquires the lock, okay, gets to access the data from the node. Okay, in that case, this, say for example, this guy got the lock, so he will put a lock on the U1 data. So until this guy releases this lock, this rate limiter should be waiting to access this data. In that case, there is a couple of like 100 millisecond of latency added to this request and response. That way, this strategy will affect the round trip time of the request response made by this user from this region. So that is again a problem. So how do we solve this problem? So we can actually solve this problem using different strategy, but they won't work truly. Say for example, we have two possible solutions. One is relaxing rate limit. This is not a real solution, but it makes you happy. So relaxing rate limit means, say out of 100 times, if you miss out a couple of times, it's okay. Say for example, a rate limit is set to 100 requests per minute. It's okay if we serve 102 or 103 requests in a minute. So that 1% or 2% of request, if it escapes, when we have truly concurrent calls happening across the multiple region. Otherwise, if you don't want to do that also, there is no real solution, because there is a problem, because we have the distributed system, there is always a latency when we sync the data between these two machines. So the race condition, right? Say for example, one request went here, and then and this guy served the request, and then also this guy updates the data from 4 to 5, right? Okay, so before this data is synced to the other node, if there is one more request made by this user, hits this, and then gets the data, so actually it gets the data as 4. It won't get it as 5. So these kind of problem are there because there is a latency between syncing the data between nodes. So we can't do much about it. So there is a little performance optimization we can still do. I'll tell you how. Say for example, so these are our rate limiter in a specific region. So instead of talking to these Redis or Cassandra nodes every time when the request arrives the rate limiter, what we can do is we can have a local memory. Okay, we can have a local memory and we can have this data placed locally in both of the rate limiter. So instead of going and fetching the data from the node or Redis node, rate limit data from the Redis node, what we can do is we can fetch the data which is available locally. Okay, and obviously we can't always rely on the local data or local rate limit data. So what also we need to have is we need to have one more service, and what this service does is it frequently syncs this local memory or local data to these nodes asynchronously. So they will be keep on updating. So there will be no direct connection from rate limit. Instead, the update or the data update happens through the service which is responsible to sync the data, the local memory data into the node and node data back to the local memory. So we will miss out some request. We will not be exactly serving 100 requests per minute. We might be serving 101 or 102, but that's okay. But we are still optimizing or we are making this performance of rate limiter better. So if you like this video, please subscribe and tell your friends to subscribe to my channel, and also leave comments or if you have any suggestions for improvement in the video, and also if you have any request for me to make the video on a specific topic, please comment and like and share. Thank you.